Welcome to this lecture on state space controller for tracking. Until now we discussed only regulatory control through state space approach. Integral mode is required for tracking. We will develop the theory for this in this lecture. We will present an example. So in addition to the standard state space model, let us consider including an integral action as given here. This is the extra state x sub I. E is the error here. It is given by r minus y of k. This expression is identical to what we use in conventional control. Let us substitute for ek. So we get this expression. In the place of y, let us put cx. Let us combine these two states. So the augmented state is given here. On the right hand side, we get this expression. You get a times xk is given here. For the second equation, we get minus ex plus xi. We have buk, but there is no uk here, so it is 0 here. There is no r here, but there is r here. So we get this expression. Here is the equation that we derived in the previous slide. Let us introduce the control law using the same nomenclature that we use for conventional control. I have used Kp for proportional control, Ki for integral mode. Let us close the loop. That means let us substitute for u here using this expression. The first term is kept as it is. For the second one, I have substituted for u. The third one is copied as it is. Let us group these two. I get this expression. And then the reference signal is here. So this is like a minus bk into x plus reference signal. This is in the a minus bk form. Let us recall the condition for pole placement. We will present an example now. Computing systems can be modeled as queuing systems. Let us consider two such queues. First queue is here, second queue is indicated here schematically. There is a buffer size of k. The first queue has a response time r1, second queue has a response time r2. They are in sequence, so the total response time is r1 plus r2. It is equal to r. R is the sum of these two, as mentioned earlier. We want to make this r to be small. It is possible to regulate the response time by manipulating the buffer size k. If the buffer size is made small, the response time will become small, but some requests may not be honored owing to overflow. The states are given here. We linearize this system at the nominal operating point. R1 bar is 2.5, R2 bar is 6.5. Here is the model numerical example that we have introduced. This is the set of values given in the previous slide. Now we want to place the poles of this system at 0.1, 0.2 and 0.3. Here is the Scilab code given here. ABC values are as given earlier. Here is the augmented A matrix, B matrix. As mentioned earlier, we try to place the poles at 0.1, 0.2 and 0.3. We calculate the controllability matrix, check whether it is non-singular. Then we place the poles using Ackermann's formula. Let us see this in the output of this given subsequently. Here it is, the output from Scilab. Here is the A matrix, B matrix, C matrix, the augmented system AA, BA. We want the poles to be at 0.1, 0.2, 0.3. Here is the controllability matrix. The determinant is non-zero, and hence you can place the poles using Ackermann's formula. This is how you place in Scilab, and we take the initial state to be 1, 1, 1, and here is the closed loop matrix. The reference signal is 1, that is, we want the states 1 and 2 combined to be equal to 1. So we add first state and second state in the previous state vector. That is why we would want that to be equal to 1, but notice that y is equal to 2. So this is how we started. If you go through the Scilab code, I carry out this loop 10 times. We implement this closed loop controller 10 times and put the state into the world state, recalculate it, and so on, and we calculate the plant output y as sum of first and second states. If I do this 10 times, you see that y going towards 1, it is not yet 1. So what I do is, manually I copy only these 3 lines and execute them. So this is how I do it. At the end of 10 iterations, you find y to be 1 as we desired, and here are the state values. To conclude, we introduced the integral mode through an extra state. We illustrated with an example. We presented Scilab code for this. I would want you to try out this code and convince yourself that this code works. So in this lecture, we introduced integral mode, which is very nice. So we have made our state space control also behave like conventional controller. With this, we have come to the end of this presentation. Thanks for joining. Goodbye.